The types of examples wobbly are cars. Very big cars going in a circle, and we say, oh wow, great, okay, why do they stay in the circle? Why do they not slide out? Well, it's a combination of that centripetal force, and it's provided by the friction at the tyres. So we do a little bit of frictional force later in class, but what we can talk about is this question here. This is a track. It has a radius of 50 meters, and the frictional force is half of the car's weight. What is the maximum speed that the car can have before it slides off the track? This is where we just use our F equals ma equation, but for centripetal motion. And we're using half of the car's weight here, 0.5 mg. That's the maximum frictional force before the car will slide out. So rearranging for velocity, square rooting, we get a lovely answer of 15 meters per second. This can be applied in other cases. So in the case before, we were looking at a car going around on a curve. This time, we're looking at banking. Banking is a way of making, being able to actually go faster around a curve because you don't have to rely just on that frictional force. You're actually getting a tan of that force. So you can have a look through this type of thing here. What you have is your weight force at the bottom, your net force here, your net force here, and this here is the normal force normal, which you would have come across before. So if you're looking at how you would rearrange this, you say, okay, well, my resultant force, or my net force, divided by my weight force is going to be tan of this angle here. You're thinking, why is that angle there? Okay, well, you've got to rearrange the angles. If you think of opposite angles, that angle there is the same as that angle there. That's theta, which means that plus that equals 90 degrees, which means theta is also that there. Which means now you can use your sine and cos rules and work out these components. We use the tan rule here. We can say, okay, tan of that is the net force over this force normal here, which is our weight force. So net force, weight force, that's tan theta, which gives us a way of describing the horizontal components. The force that keeps the car on the curve is still this mv squared on r, the centripetal force, and it has to be equivalent to mg tan theta, which you can then rearrange to get tan theta by itself, and you'll see our mass disappears. So the angle of the banking depends mostly on the speed and the radius of curve, but not on the mass of the vehicle. It's the same for all vehicles, which is why a truck going around the corner is going to have just the same amount of effect as a car. If you go too fast, you need friction to prevent you sliding up the curve. If you go too slow, you need friction to prevent you from sliding down. So here's an example of motion in a vertical circle. At the bottom, you have forces acting on the object, such as the weight force, and you have the tension, which is opposite the weight force, opposing the force. So if you combine both the centripetal force, which is due to the velocity, and your weight force, you have a resultant force, which is towards the center. At the bottom, tension provides the centripetal force and support the weight of the object. So you've got your centripetal force here, you've got your tension in your string minus the weight, so that's the tension here minus the weight, which is in the opposite direction, has to equal the centripetal force. What happens now at the top of the circle? Let's have a look. The tension action at the top of the circle is both again the weight and the tension in the string. But the tension in the string is now in the same direction as the. So when we add up all our forces, we get the tension plus the weight has to be equal to the centripetal motion. The centripetal force. Because that tension is less than at the bottom, then the weight provides some of that centripetal force. So we can get things like what the feeling of weightlessness if your centripetal force. If you're going fast enough, you can feel weightless at the top, which is particularly important when you're designing, say, I don't know, roller coasters, such as this one. So what's happening here? We have 2 points, A and B, which are a certain distance apart, which is 10 meters at the top, and the radius of the track is also 10 meters. I'm giving a car of mass 500 kilos. We're also just going to use G as 10 meters per second so that we can find the G forces at A and B. So really this is trying to find the resultant forcing, assuming that there is no energy loss. The first thing we have to do is actually figure out what is the velocity. So what we're going to do is say, what is the potential energy here? And it's going to be converted into kinetic energy down here. If we do it that way, our potential energy, mgh, is equivalent to half mv squared, which just gives the velocity being the square root of 2gh. Now this is important because the height is different at A to B. So the height that the thing travels here is, in the first place, is going to be 30 meters, 10 plus 20. So our first velocity, and I'm actually going to put it in terms of velocity squared, velocity squared is going to be 600, which is 30 times 10 times 2. That's at point A. At point B, our velocity squared is going to be different because we've only travelled 10 meters. And what we're assuming is that the car comes down to bottom at point A, travels all the way up to point B, doesn't lose any energy on the way. So if that's the case, then here at point B, it's 200 meters. Well, 200 meters per second squared. Meters squared per second squared. So, at the bottom, what happens? We have the mass of the car, the resultant force, and the centripetal force. So, we found our velocity at the bottom to be, well, velocity squared was 600, so the square root of that is 24.5 meters per second. Now, our resultant force minus our weight force is equivalent to that centripetal force. What is our resultant? Well, we can work out what the resultant is by putting in the mass of the car. 600 times 500 divided by 10. That was 600 was our velocity squared, times 500, which is our mass, divided by 10, our radius, plus 10 times 500. That's basically just bringing that mg to the other side of the equation, which gives you, well, 35 kilonewtons. But if we don't use the mass of the car, then we can actually find R with respect to G. So R in terms of G, which is really what we're looking for. We're looking for the G force. So our force is 35 kilonewtons, but our G force is 7. So that basically means it's 7 times bigger than gravity. At the top, what happens? Let's see. Our resultant force is now down in the same direction as our mass. Our energy change here gives our velocity to be 14.1. Remember, velocity squared is 200. So, in this case, our resultant force and our weight force add, and they have to be equivalent to the centripetal force. So if we add those up, we get the 500 times 200 divided by 10, which is this part here, minus, in this case, the mass times the weight, so 500 times 10. And this gives us 5 kilonewtons. Again, we can do this in terms of G, where you use the same equation, but you've got 10m over 10m, which gives you 1g. So at the top, you're going to have a G force of 1. We can also use centripetal motion in terms of gravitation. So there's a gravitational law, which is basically the force between two masses. And in this case, it's two large masses, so you might be talking here, in this case, about the Sun and the Earth. But this is actually a force that occurs between any two masses. The bigger the masses are, well, the bigger the force. But any two masses will have this sort of force, even electrons and protons. So, is the force sufficient to cause Earth's circular motion? Now, we know a lot of the things already about the Earth. So we've got, this is our gravitational constant, 6.6 times 10 to the minus 11, which is big G. The mass of the Sun is about this, 2 by 10 to the 30 kilos, and the mass of Earth is 6 by 10 to the 24. And we're going to divide by the radius of the Earth. So, actually not the radius of the Earth, the orbit of the Earth around the Sun, which is 1.5 by 10 to the 11. And so you're going to square that back, and you get a force of 3.56 by 10 to the 22 newtons, which is an enormous force. And you think, well, big deal. Let's see if this is equivalent to Earth's motion. So if we set this force to be mv squared on r, or we use the alternative formula and we use 4 pi squared mr on t squared, then we can compare it directly to the period. So 4 pi mr on t squared, our period is what? That's the mass of the Earth times the radius between the Earth and the Sun, and our period is 365 days times 24 hours in a day times 60 minutes times 60 seconds to get it into seconds, which is what it's normally measured to. And now you get 3.56 times 10 to the 22 newtons, which is exactly the force that you got there. So the gravitational force is sufficient to keep the Earth revolving around the Sun with a period of 365.5 days. This is basically where our laws came from. People fiddling around with the mathematics worked this out. But we can use it for new things, such as satellites. So if you've got a satellite of mass m that's moving in a circular orbit around the Earth with a constant speed and a height of, say, 1,000 kilometers, we're talking 1,000 kilometers above the Earth's surface, what would the orbital speed be? We can use the same equations. What we're doing is we're equating our centripetal force with our gravitational force. So let's see, if we rearrange our equation, we actually cancel out the mass of the satellite, and we're left with v squared equaling gm on r. G was 6 by 6 by 10 to the minus 11. I'm actually using a slightly more detailed form here, 6.67. And our mass of the Earth is 5.98 times 10 to the 24. So before we use 6 by 10 to the 24. And the radius here is 6.38. That's the radius of the Earth. But remember, our satellite is 1,000 kilometers above the Earth. So that's 1,000 times 1,000 meters, 10 to the 6. So that means we have 6.38 plus 1 times 10 to the 6. So we get 7.38 meters as our radius. Equate them out, and we get a velocity of about 5.4 by 10 to the 7 meters squared per second squared, or 7.35 by 10 to the 3 meters per second. So that's about 7,000 meters a second. It's pretty fast. And really, you should note that the velocity is independent of the mass of the satellite. We didn't need to include that in any part of our equation.